Welcome back. This is going to be kind of a fun lecture. So we've been talking about how to integrate nonlinear differential equations x dot equals f of x, things like the Lorentz 1963 butterfly attractor system. And today I'm going to show you how, instead of integrating a single trajectory along that system, we can actually integrate a big bundle or a cube of initial conditions and integrate them all along the system. I'm actually just going to run this code. I'll walk you through this in a minute, but this is the kind of thing I'm going to talk about, is how do you take a big cube of initial conditions and integrate them through this differential equation all at once to see where they go. So this is a very, very useful thing to do in dynamical systems, is not to just look at one trajectory, but to look at kind of a bundle of nearby trajectories. At least in chaotic systems, I find that useful. And I'm specifically going to talk about how do we do this in a way that is efficient in languages like Python and Matlab that are not compiled, because the naive way you might think of doing this by writing a big for loop is totally going to grind your computer to a halt, or at least it could. So I'm going to talk about why we would want to integrate more than one trajectory at once and what that means physically, and also how to compute these things efficiently in languages like Python and Matlab. And when I say compiled, you know, when I was a kid growing up, computers were so slow, it really mattered that you compiled your code into machine code, you know, assembly code that would then run at a low level on your computer. Now, a lot of times, a lot of my students don't even know the difference between compiled code and interpreted code, because, you know, it's still so fast to run MATLAB and Python most of the time, even though MATLAB and Python are not pre-compiled languages. You don't write a code, then hit compile and have it, you know, optimize it into really efficient assembly code that runs on your processors. It kind of does that on the fly as needed. That's an interpreted language. And that can be really, really slow if you have a bunch of nested for loops, for example, to walk through all of these initial conditions. That's an example where you definitely don't want to do that in Python or MATLAB. And instead, if there's any way to leverage a vectorized operation or a matrix vector product or anything that's kind of in terms of linear algebra, then you can use these. So MATLAB and Python are both built on top of some compiled Fortran linear algebra codes. And so if you can access those kind of linear algebra routines by coding this up in a smart way, your code could be, you know, tens, hundreds, thousands of times faster. Okay, so pretty important thing to know if you're getting serious into computation is how to compute things in an efficient way using vectorized operations when your language is not compiled. If this was compiled C code or Fortran code, it really wouldn't matter if I had nested for loops, because it's going to optimize that pretty efficiently anyway when it compiles it. Okay, I'm going to run this one more time because it looks super cool. What I'm doing here is I'm starting with an initial condition 0, 0, 0. And I'm creating a large cube of initial conditions of, you know, side length, you know, minus 20 to 20, so length 40 by 40 by 40. So that's what I'm doing here. I think if I just run this code, you'll see this is my initial cube in blue plotted on top of the Lorentz attractor. And when I run the code, it's going to integrate all of those particles forward in time very, very quickly. So it's kind of just cranking through and running these pretty quickly through this differential equation. I believe this is my fast code that's leveraging those kind of vectorized compiled Fortran guts in MATLAB. I'll tell you how in a minute. But you can see cool stuff happens. That cube initially starts off of that white Lorentz attractor, and very quickly it kind of glues on and adheres onto this attractor. That's why it's called an attractor, because it attracts these blue points, and then they kind of mix and smear onto that attractor. Okay? It's also called a strange attractor. And what I find cool is that you can also kind of decrease the size of that cube of initial conditions. So maybe I want to look at this little cube right here. So you can see, I think, just a little teeny bit, this blue cube right here. And what we're going to do is now we're going to integrate that cube forward. And you can almost think of that as a little bit of uncertainty on that initial condition. You can think of this as an initial condition with some uniform uncertainty in x and y and z. And you see that as time goes on, eventually that uncertainty causes those trajectories, even though they started close, eventually they go to very, very different places. And that's what we mean by chaos and sensitive dependence on initial conditions, is even though that cube of particles started close by to that initial condition, after some amount of time they kind of smear out to very different places on this attractor. And I can do this for an even smaller cube of particles. Now this has length 0.1, and I don't think you can even see it. It's teeny tiny. But if I run this code, you're going to see this thing moving around. And so now you can see my little blue particle. That's actually a whole bundle of trajectories moving around. But because they started at such a close proximity, they stay close to each other, they shadow each other. But eventually they're going to start stretching pretty much when they hit this saddle point. There's a saddle point in this dynamical system right about there. And when those particles got close to the saddle point, they sheared and they started stretching out. And again, that sensitive dependence on initial condition, that's a hallmark of chaos, that's often driven by saddle points in the flow that kind of spread out particles. Even if they start very close, the saddle shoots them out to different lobes of the attractor. So these are the kinds of things we might want to compute and look at and analyze, is running a big bundle of trajectories through the code. If I do this using my slow code, you'll see that it runs a lot slower. So I'm just going to run my slow code that's doing this with for loops. You can see that it still is going, it still is integrating the solution, but it's kind of much, much slower than it was in the other case where it was already mixed and folded by now. Okay, so this code is taking that initial cube of initial conditions, and it's literally writing a for loop. Let me see if I can do this in a place that's not going to irritate me later. For my cube of initial conditions in x, in y, in z, it literally created I'm literally going through a for loop. This is the I index for the x particles, the j index for the y position of the particles, and the k index for the z or z position of the particles. And I'm writing a big nested for loop. For I equals 1 to 40, for j equals 1 to 40, for k equals 1 to 40, integrate this trajectory, integrate that trajectory, integrate the next trajectory. And that's what's happening here. It's very, very slow. It's very, very inefficient, okay, because for loops in a non-compiled language like MATLAB or Python are typically very, very slow, because it's kind of every time, inside of that for loop. So I've got like for I, for j, for k, integrate. Every time inside of this loop, the code is kind of locally compiling this instruction here, which is very expensive, and it's doing that every single time inside of this looping through this cube, and that's why this slow code is grinding to a halt. It's very, very slow. I wrote this code 10 years ago to show my undergrad class, in intro scientific computing class, and it ground to a halt even slower 10 years ago. So this is actually, for me, relatively fast compared to how slow it was when I wrote this code 10 years ago, but it's still slower than the vectorized version. And just to remind you, this version here, I'm just going to comment these guys out. So we're comparing apples to apples. My vectorized version is, like, you can see it just ripping through these particles, cranking through, because it's not based on this nested for loop. It's integrating every single chunk of particles. It takes this whole cube of particles, and I'm basically finding a clever way of writing that RK4 single step, so it crunches through all the points at once. It computes using linear algebra, compiled Fortran linear algebra. It's stepping all of these 1dt forward at once, which is way more efficient than this for loop. So let me get into the code and show you real quick. I'll just go through the slow Lorentz first because it's easier. It's just a bunch of for loops. So I have my grid of initial conditions, which in MATLAB and Python both, I believe you just use this mesh grid to create this kind of cube given a mesh in x and y and z. And then our initial conditions are going to be that big cube of particles. I'm going to scatter plot all of those particles so you can see the cube. And then the trajectory is really easy. You know, we're going to integrate in increments of 0.01 up to a big T of 4, and we're going to step through this time index L. And then for each index, for I, for j, for k, I think here I call it for 1 to the length of the x vector, for j equals 1 to the length of the y vector, for k equals 1 to the length of the z vector. That's just a big nested for loop. What I'm doing is I'm taking that initial condition, that defines a single initial condition, and that single initial condition is literally the I, j, kth position of my array of particles. I'm stepping that forward using my RK4 single stepper, and I repeat and I repeat and I repeat for every point in z, in y, in x, and then in time I do this thing. And again, nested for loops are a nightmare in MATLAB and Python, any language that's not compiled, because what it's doing is it's kind of compiling this on the fly every single time. So it's doing that like thousands and thousands and thousands of times, very expensive. In a compiled language like C or Fortran, this would be totally fair game. It'll compile this into something super efficient, and it won't be slow, any slower hardly than doing the vectorized calculation. So this is the slow code. You should avoid doing big nested for loops if you can, and instead you should do vectorized operations. And actually, my RK4 single step, the way I wrote it, if I can bring this code up really quickly, it actually is written in a way that's incredibly general. So this why not does not just have to be a vector of initial, like an initial condition. It can be a whole 4-dimensional tensor, like an array of initial conditions, or a kind of a matrix of initial conditions, or a cube of initial conditions, if you like. And nothing in this code changes. It'll basically output the time derivative, ddt. I'm sorry, it'll output the next time step of all of those points. So if y naught is a single initial condition, it'll advance that one time step forward. If y naught is a huge cube of initial conditions, it will update all of those cube of initial conditions into y out. It'll step them all forward in time. As long as this function, my right-hand side function, x dot equals f of, in this case in MATLAB and in Python it's defined as t comma x. As long as my differential equation, as long as this function fun on the right hand side is defined so that it can take in an array of x's and evaluate them all at once to give you an array of dx dt's. And so that's literally this code does that. And when I go to Lorentz fast and I define the same grid of initial conditions and I am plotting them, here what I'm doing is I don't have a big nested for loop for all of these particle positions. I just have a loop for time. I'm time stepping from dt to dt to dt. And at each step, I use this Lorentz 3D code to return dx dt at this entire cube of initial conditions. So this is a custom code I wrote here, Lorentz 3D, that returns the vector field at every single initial condition. And RK4 single step can use that to walk these all forward all at once. And this is going to be way more efficient because it's using just matrix multiplications, which are using compiled Fortran code. So if I go into Lorentz 3D, this code, it looks a little nastier than Lorentz. Maybe I'll pull up Lorentz just so you can compare. Lorentz was pretty simple. It took in a single point x, a single position, x, y, z, and it returned dx dt, which is a 3 vector. And Lorentz 3D is exactly the same code, except it says, this x, x1, x2, x3, and it returning dx. Those can be arrays of initial conditions. So I have my y2. This is a cube of I, j, and k indices of y, of x, of z, and it's going to return this big y dot for all of those initial conditions. So you can convince yourself that these, comma, colon, comma, colon, comma, colon, this is basically a big array of initial conditions in y, and it's going to return a big array of dy dt's that my RK4 single stepper can work with. And everything here is just matrix algebra, so it's going to be really fast, really efficient compiled Fortran code. And so again, I'm just going to run this one more time so you can see the impact of, this is the slow algorithm. In the olden days, it was like one update, then another update, Then another update. My computer, must be about 8 times faster now. Okay, but this is still slow compared. Let me close all. Compared to using this fast vectorized calculation. That's what it's called when you leverage this matrix algebra. It's called vectorization. And this is the vectorized code. It's way, way faster, way, way better. Okay, I love this example. I like this also because it shows you things you want to do with chaotic systems. I want to run a grid of initial conditions through to see how it behaves in time. And maybe I'll do my, I'll integrate for a little bit longer because I can, because it's fast. And I'm going to use my smaller set of initial conditions that have, so this one was minus 20 to 20, that big, big cube. This cube is teeny tiny. It's minus 0.1 to 0.1 around my initial condition. So this is a much tighter initial cube. Whoops. You should be able to see it. And we can see this little blue cube of initial conditions whipping around. It's staying pretty coherent because the original, uncertainty in my initial condition was pretty small, minus 0.1 to 0.1. But eventually, when it gets by that saddle, it starts to shear and stretch, and eventually it's going to fold and stretch on this chaotic attractor. That's what it means to be chaotic, is initial conditions that start really close to each other eventually smear out and go very far away and are kind of indistinguishable after a long enough time t. And that's what you see here. I also think this is kind of cool because in this example, the view is rotating, so you can kind of see it. It looks neat. So this is an example of things you can code up yourself if you want to. And by this point in time t, all of my trajectories are kind of all spread out kind of chaotically across this tractor, and it would be very hard to tell which one came from where in that little initial cube. Cool. OK, so that's this example. All of this code is in Python also. So Alan Kaptanoglu ported this code over to Python. I'm not going to go through all of the guts again because this is not about the coding. It's about compiled versus non-compiled and uncertainty and vectorized versus non-vectorized. It's the exact same story in Python, really, to be honest. So this is Alan's code in Python. Again, we're going to use this RK4 single step. And the slow code is going to use this massive, massive nested for loop of for I, for j, for k. And this is going to be very, very slow. He actually uses the time command here to compute exactly how long this takes to run, which I think is nice. So you can quantitatively compare the time of the slow algorithm and the fast algorithm. And then the fast algorithm here, oh, this is the fast one, I'm sorry. No, this is slow. This is the slow one. I'm confusing myself. The fast one, again, RK4 single step doesn't change. I wrote this code to be generic so it could take a big array of initial conditions. And this is actually a good exercise for you, is to convince yourself that this code still would work. It would still update as long as, even if y naught was an array of initial conditions, as long as this function returns that same shaped array of dy dt's of the right-hand sides. And it looks like in Python, you don't even have to change the Lorentz function, unless I'm confused about something here. And here, essentially, in this fast version that Alan wrote, this RK4 single step is being applied to that Lorentz vector field, but on this massive array of initial conditions. And so this is actually nicer in Python because you don't have to modify this Lorentz function to return a vector of dy dt's or dx dt's. It apparently already works to return that. And I'm going to say that again, RK4 single step will work on this cube of initial conditions as long as my right-hand side function, my Lorentz function here, returns the same shaped cube of dx dt's or dy dt's. And so that's what's happening here. And now you see that his code was way faster. The slow code took 14 seconds. This code took 0.08 seconds. So way, way, way faster, 2 orders of magnitude faster. once you use this vectorized computation. So really, really cool. And again, this gets on a lot of the aspects that I want you to be thinking about. What happens in a chaotic system when I have nearby initial conditions, they stretch and fold. But not only that, how do I do that efficiently in my language of choice like Python or Matlab if they're non-compiled languages? Okay, cool. That was what I wanted to show you, so thank you for listening.